This assignment demonstrates how to solve complex math problems using completing the square and partial fractions. These methods help us simplify half equations so we can calculate the definite integral, which represents the total result over a specific range. In the real world, these techniques are essential for engineers and scientists to understand system stability, break down complicated electronic signals, and measure total energy or profit.
First, let's look at the denominator of our first integral, negative x squared plus 4x minus 5. To evaluate this, we use the completing the square formula, where a equals negative 1, b equals 4, and c equals negative 5. We factor out the negative 1 and follow the formula. This is the completing the square formula. Plugging in our values, we get negative 1 in bracket x minus 2 square minus negative 2 square plus 5. Inside the bracket, this simplifies to x minus 2 square plus 1. When we distribute the negative 1 back through, our final expression is negative x minus 2 square minus 1.
After applying completing the square method, the denominator we get like this, and I substitute this back into the integral. Next, I factor out the negative sign from the denominator by extracting the constant 2 from the top and the negative 1 from the bottom. I move them to the front of the integral. This gives us a coefficient of negative 2 outside. Then, I use the use substitution method. I let u equal x minus 2. Since the derivative du over dx equal 1, it means du equal dx. This allows me to rewrite the integral in the standard form. Negative 2 integral of 1 over u squared plus 1 du. Using the standard integral formula, this results in an inverse tangent function. After substituting u back with x minus 2, the final expression is negative 2. Tan inverse x minus 2 evaluate from 1 to 4.
Finally, we evaluate the definite integral, negative 2 in brackets tan inverse x minus 2. From the limits 1 to 4, we apply the fundamental theorem of calculus by plugging in the upper limit first. Negative 2 in bracket tan inverse in bracket 4 minus 2 minus tan inverse 1 minus 2. This simplifies to negative 2 tan inverse 2 minus tan inverse negative 1. Using the AKMAL values, this is negative 2 in bracket 1.1071 minus negative 0.7854. After adding the terms in the bracket and multiplying by negative 2, our final answer is negative 3.7850.
For the next question, we need to evaluate this equation using partial fraction up to 4 decimal places. First of all, we need to set up their partial decomposition by finding their constant and linear. Take a look at this. We got 5x squared as an a constant, while 2x plus 7 as a constant bx plus c. As for linear, we're going to separate x plus 2 with a constant a and x squared plus 4 for a constant bx and constant c. After that, we got this equation as our constant and linear. Next, we're going to move the x plus 2 and x squared plus 4, which at the left to the right, to match with their constant. So we got this as our answer. Then we need to expand x plus 2 and x squared plus 4 we already put in the right, in the each of the constant, and we got this one. As you can see, from this constant, we can simplify some of this. Just cut this one and this one, so we can get this as our next equation.
Now, let's move to our partial fraction decomposition to find the constants a and c. We start with our expanded equation. 5x squared plus 3x plus 7 equals a in brackets x squared plus 4 plus b in bracket x plus 2 plus c in bracket x plus 2. To isolate a, we let x equals negative 2 because it makes the b and c terms 0. This leaves us with 21 equals 8a, which means a equals 21 divided 8. Next, to find c, we let x equals to 0. The left side becomes 7 and the b terms disappears. By substituting our value for a, we get 7 equals 21 divided 8 in bracket 4 plus 2c, which simplifies to 7 equals 21 divided 2 plus 2c. Subtracting 21 divided 2 from 7 gives us negative 7 divided 2. equals 2C. Dividing by 2, we find that C equals negative 7 per 4. Divide 4.
We already found A and C. Now we're going to find B constant for B. So we're gonna let X as a 1. So we're going to change in any X into a 1. After that, we're going to simplify it. So we get 15. A constant with 5, B constant with 1 and 3, and C constant with 3. Then we're going to change constant A and constant C with the answer we got early. So we get 21 per 8 as a constant A and negative 7 per 4 as a constant C. And we solve it and we get this answer. Since we're going to find B, we need to put the B on the right while the another number on the left. So we're going to solve it and we got 57 per 8, and on the right is 3B. So from the 3 on the B, we need to put with the 57 per 8. So we got 57 per 8 divided by B. So we got B is a 90 per 8. Since we got B, so we can put the complex constant A, B and C into equation. So we got this as our answer.
After applying partial fraction decomposition, we have transformed the original complex integral into 3 simpler terms and pull out their constants. This allows us to solve the problem step by step using standard integration rules. For the first term, we pull out the constants of 21 over 8, which leaves us with the integral of 1 over x plus 2. By using the natural log rule of integral 1 over ax plus b dx equal to ln ax plus b, we can directly integrate this to 21 over 8 ln x plus 2. Next, for the second term, we have 19x over 8 times x squared plus 4. We use u substitution by letting u equal to x squared plus 4. Differentiating gives du equal to 2x dx, which we rearrange to x dx equal to du over 2. Substituting this back, the integral becomes 19 over 8 integral 1 over u times du over 2. Remove the 1 over 2 and multiply it by the constant. Thus, by using the natural log rule of integral 1 over x dx equal to ln x, this simplifies to 19 over 16 ln u, then 19 over 16 ln x squared plus 4 once we switch back to x. Furthermore, the third term is negative 7 over 4 times x squared plus 4. This follows the inverse tangent rule of integral 1 over x squared plus a squared dx equal to 1 over a inverse tangent x over a. Here, a squared equal to 4, so a equal to 2. Thus, we multiply our constants negative 7 over 4 by 1 over a, which is 1 over 2, giving us the final answer of negative 7 over a inverse tangent x over 2. Hence, we combine this into one antiderivative and apply the fundamental theorem of calculus by evaluating the expression at our upper limit of 2 and subtracting the value at our lower limit of 1.
Next, to get the final value, I am evaluating this expression between the limits of 1 and 2. I substitute the upper limit of 2 into the function, which gives us 5.4211. Then, I substitute the lower limit of 1, which gives us 4.3894. Subtracting the two values, we get 5.4211 minus 4.3894. The final result is 1.0317.
So for the application for both of the question we solve it, we use 3 core mathematics tools to solve a complex engineering problem. So first of all, we use completing the square to find the center and stability of the system, which is essential in physics for identify the peak of a projectile pad or the equilibrium of a structure. Next, for the partial fraction decomposition from the question we solved earlier, we use in a complex system, similar to how electrical engineer breaks down to complicated signal into its individual component to analyze circuit behavior. Finally, by evaluating these definite integrals, we calculate the total effect of that system over a specific range, just as an economist will calculate total profit or an engineer will measure total energy consumption over time.